Hello friends, welcome back for another video of Simple Haskell. I figure today what we'll do is we will talk about how to define our own types. I was originally thinking about doing numerical types in this, but I think that's best saved for a video of its own. And yeah, so without further ado, I mean the real primitive types, just to kind of get it out there, is really just char and int, or the numbers themselves, which again we will explain more in a later video. But so let's start with bool. So data bool is defined as either being true or false. So this is, we could of course create our own boolean. So let's call it boolean, and we want to call it T or F. And we do this because we like the word boolean, and we would rather not write true or false because we already spent all of our time writing boolean. And so what is notable here about how we define this type is that we have multiple options for this type. And so we can note that by the bars. And so for another type that we could come up with, we could have any sort of number of cases. So you could say data operating systems is Windows, is NixOS, my favorite, and I'm just gonna say generally Linux. NixOS is Linux, so this is a bit of a lie, but and then Mac. So if there was more operating systems, we could continue writing out our options. And again, I don't think there's much more to say about this sort of simple thing here. Now, there's the data keyword, the type keyword, and the newtype keyword. Those are our three tools for building out our type system and defining our domain. So type is really, type means a type synonym. So as we saw with the last video, string is a type synonym of a list of char. Char being a primitive data type, and list being a pretty primitive data type. A complex but primitive data type. And we just, the reason for this is we just want to call it a string. Everyone knows what a string is. You might not immediately think about a list of char, but that's actually what a string is just a list of characters. So, we could also create a type synonym for computer system, and it is operating system, which I'm going to change the name of. And that really does nothing besides allowing us to call an operating system a computer system as well. Don't think there's much more to say there. That's how it works. It's a pretty simple rule. Yeah. And then we have newtype. So newtype is very similar to data, except it's a little more constrained. So a newtype, if we were to try and say operating system, I'm going to say operating system prime so that it doesn't complain. Is going to complain. Oop. Well, I should also complain about that. Oh, you know what? I gotta. Come on. There we go. We will see a complain that a new type must have exactly one constructor. So the real application of a new type is really just to often it's used to override certain behaviors about a given type. So we might have, for example, new type password, and this new type password constructs a string. And so we don't want to have our password just be a random string floating around in our program. We want to make it very explicitly clear that it is a password. And as we'll see with type classes, there's a type class called show. And so show, show obviously just turns anything to a string. And in the case of password, we don't want the value contained in password to ever be printed to, the logs or some accidental giving up of said password. And so that's one way in which we can control that, just by using our data types. And so now I guess that really gets us into our higher kind of types. So, and actually, no, not exactly yet. So let's say we have, what's a good example here? Well, if we were to take operating systems and we expanded on it to say, let's actually make this a little bit different. We're going to say Linux and a flavor of Linux. XOS, Ubuntu, Mint, Kali. So that is one way we could get a little bit more complicated with our data types. We could say that we have the full array of operating systems, and one option is Windows, plainly, Linux with a given flavor. So this could read as Linux NixOS, Linux Ubuntu, Linux Mint, Linux Kali. And so if we just logically think through our cases, if we were to pattern match on every single type of operating system, we would have 6 different options to choose from. Windows, and then the 4 Linuxes, and then Mac, making 6. The one way it can get more complicated, or that we can do more with our types, is by moving actually away from what is a concrete type. So everything here is directly usable in a case statement. We can pattern match on anything here. We could say case operating system of Linux Mint. Do something. Windows, do something, right? That is all still possible with all that we've done. And of course, for types, we would be pattern matching, or the type declarations, we would be pattern matching on what the real type is. Those actually get thrown away at compile time when we no longer are thinking about a program and it's being turned into a binary. Now, moving away from that into a bit more freedom, we saw something like this in the last video. Data either A, B, where we have left A, right B. So we still have, the right B still operates in the same way as Linux. We can make it that way if we were to say right, let's say a string. We give it a very real string. And there is no options for what that right can construct. However, we don't want that. We want to have either A, B, so that we can use either and all of its behaviors, which we will learn more about, by having this be a higher kind of data type. So this means that we can have in a type signature where let's say, we're just taking a string for some reason, and we can then return either string int, or maybe it's either string puzzle, either string, either string int. And it can literally be anything, so long as it's a concrete type. And so, we could not give this. That would be a non-concrete type, and we have to actually give it a concrete type. So now, if you are familiar with polymorphism, pretend what I'm saying doesn't have some faults in it, because there is a bit of a lie I'm saying. So, but effectively, we have to end up with something like this. And it's still true even in the sense of polymorphism. We have to end up with a concrete applied type of either. You could see, now with polymorphism, you could see something like this if we're, let's say, building a general function, which, we're defining some sort of maybe failure behaviors for, that we can use for a number of different functions, but in our actual application, we will at some point boil down to a concrete type of either string int, or either string puzzle, or something, or either string operating system. So, and we can see, so the possibilities that are, possible with this is now a lot greater, because this means that any two concrete types in the Haskell universe can fit into this. We could even have it be the opposite way around if we really wanted to. There's no constraint here. But you will typically see that it's either string or either error. And so it has a very particular use case. And that's the core of what the type building system is in Haskell. Through any of these rules, we can figure out what would be a valid type in Haskell. So we could even just now for the sake of argument, and since we have a little bit of time left before we hit 15 minutes, we could do this, and we don't have to use the A here if it's in the head, right? This being the head in terms of lambda calculus, and this being the body, we don't have to use everything in the head, and that's just standard lambda calculus. However, let's say we wanted to do C. We wanted to use a variable C that does not exist in the head, then we cannot do this. It's going to crap out and say, what the heck is C? We are simply parameterizing it with what we see in the head. And I believe that is it. The one thing I'll add, just because we do have a bit of time, is that there is another kind of type practice you will see, where let's say we have this password, we'll use a record, and so we'll have this generated function. So we define it as this, and then what we would see is that if we look at the type of, can I do this? Where is that? So annoying. Come on, man. All right. There we go. So if we were to look at the type of get password, we would see that it takes a password and gets the string. So this is going to retrieve us this string contained in here. And that is it. We have record types talked about as well. And of course, we can have multiple records in here, like A is a type int. We wouldn't actually want to use it here, but we could do this for sure. And then A and B would become their own functions as well. That is everything in terms of what actually matters for the basics of Haskell types. Thank you so much for watching. Hope this was short, explanatory, and to the point, as well as helpful. Bon voyage and happy coding.